Here we will talk about the smooth mapping in manifold. This is the generalization of smooth mapping in Euclidean space. This is the generalization of smooth mapping in Euclidean space, because in Euclidean space we know that a function is smooth if all of its components are smooth. But in manifold theory this does not hold, because in manifold there does not exist any coordinate. It has coordinate but it's locally. So to define the smooth mapping in manifold, we have to define it by its coordinates or charts or atlas. Okay. So here we have seen that if M is a manifold and P be a point, so and we have taken the U be an open neighborhood of P, and phi is the homomorphism from U to some open subset of Rn, that is phi of U. So basically here U comma phi is a chart of P. Okay. Now here F is a map from M to R. So here we say that the function F is smooth if the function F composition phi inverse is smooth. So here the definition is, let M be a smooth manifold. A function is said to be a C-infinity map, that is smooth map, at particular point P if there exists a chart U comma phi about a point P such that phi composition U is phi inverse and that's acting on phi of U to R. So basically here phi composition phi inverse is a mapping from Rn to R. So basically here it is the mapping in Euclidean space. So we have a function in manifold, so we transform the function from manifold to Euclidean space, then we talk about the smoothness of the Euclidean space of that function, and then we go back to this manifold. Okay, and so here if this function f compose phi inverse is smooth, then we say that f is smooth at that point P. Now if the function f is smooth at every point of the point of the manifold M, then we say that f is C-infinity map on the manifold. Now we have seen that the definition, the smoothness of a function, it depends on the chart. We have seen that the function smoothness condition of the function is totally independent of the choice of chart. So lemma, let function f be from R to R be a smooth function and v of psi be a chart. Then f compose psi inverse is also smooth. So in this lemma we are proving that if we have a smooth function, then if we have another chart, that is v comma phi, then this function if compose psi inverse is also smooth. So if a function is smooth in one chart, then it is also smooth in another chart. So basically here the definition of smoothness is independent of the chart. Yes, here's the proof. Since the function if is a smooth function, so there is a chart u comma phi such that if compose phi inverse is smooth. Now u comma phi and v comma phi are smoothly compatible, because in the manifold we have given the differential structure, smooth structure. So that's why these two charts are smoothly compatible. Therefore, f compose psi inverse equal to f compose phi inverse composition phi compose psi inverse. So this composition is equal to the f compose psi inverse. So here we have proven that f compose psi inverse is smooth function, because in this right hand side of this equation it is f compose phi inverse. We know that since f is smooth, so f compose phi inverse is smooth, and the later part is that psi phi compose psi inverse. Since the two charts are smoothly compatible, so this function is smooth. So we know that computation of the smooth function is smooth. So basically, f compose psi inverse is smooth function. Now we have talked about the smooth function in a manifold to real number. Now we will talk about the smooth function between two manifolds. Let's suppose m and n be two smooth function, and if from m to n be a map, then we say that if it is a smooth map, if for each m point p belongs to m, there exists a smooth chart u comma phi containing p and v comma psi containing fp, such that f of u belongs to v, and the composition map psi compose f compose phi inverse is smooth from phi of u to psi of v. So here again the same thing happens. The function psi compose f compose phi inverse. This is the map from Rn to Rm. This is the map between two equivalent space. So here basically we are talking about the smooth function between two equivalent space, and you transfer this map to the manifold. So we are giving the definition of a smooth map between two manifold by using the smoothness condition of that function in two equivalent space. Okay, here is the picture. Here the left hand side is the manifold M and the right hand side is the manifold N, and we are giving a function f, and in M we have a point P and open neighborhood Q, and in N there is a point, we have point FP and open neighborhood V. Okay. Now P, there is a chart P of about P, that is U comma phi, and there is a chart about FP, that is V comma psi. Now this map phi psi composition F composition phi inverse, this is the map from phi of U to psi of V. So this map is smooth, then the function f is smooth. Now we have the notion of diffeomorphism. Now let M and N be two smooth manifold. A diffeomorphism from this two manifold is a smooth bijective map that is also a smooth inverse. This is the same notion of homeomorphism, where in homeomorphism we have seen that two spaces are homeomorphic if we have a function that is bijective and continuous, and its inverse also continuous. Okay. This same notion here in diffeomorphism, but it is a more stronger condition. Now two manifolds are said to be diffeomorphic if there exists a diffeomorphism. Now consider the following mapping function f function from Bn to R. Here Bn is the unit n-dimensional sphere, unit n-dimensional ball, that's it, and here G is from Rn to Bn, and the function fx is defined by x by root of 1 minus mod of x square, and G function is defined by g of y is equal to y by root over 1 plus mod of y square. These two maps can be easily seen that they are smooth and they are inverse to each other. So here we say that the Bn, which is the n-dimensional ball, open ball, and Rn, they are two diffeomorphic. So here we can say that if the two spaces are diffeomorphic, then easily we can conclude that the two spaces are homeomorphic. But the inverse is not true always. Okay. Later we will see that if two spaces are homeomorphic, then they are not diffeomorphic. And now a very interesting question arises whether a given topological manifold admits a smooth structure that are not diffeomorphic to each other. Now consider two differential structure in real line. The real line R, identity map. This is identity map. This is we know that identity map is homeomorphic. So this is the atlas differential structure, smooth atlas in real line. And there is another, this R, phi, where phi is defined by phi of y equal to y cube. Now the function f is defined, the R comma identity map. This is the first the real line with each atlas is the identity map, and to the R comma phi the here difference structure is the YQ, and the function is defined by f of y equal to y to the power third on the it is an differential. Since the map the phi compose f compose identity map inverse and the identity map compose f compose phi inverse, they are smooth. So these two different structure they are diffeomorphic to each other. So here it can be easily proved that if the set of real line it has only one smooth structure up to diffeomorphism. Now basically the question arises that is there any topological manifold which has the different structure, and is there diffeomorphism or not? So this question is partially solved by Monquets and Moos. They prove that every topological manifold of dimension less than or equal to 3 has a smooth structure that is unique up to diffeomorphism. And but for high dimension case, this is also still an open question. In the equivalence space, except for dimension 4, it's unique smooth structure. But for dimension 4, the equivalence space has uncountably many different smooth structure. John Milnor in 1956 showed that there are smooth structure on 7-dimensional sphere that are not diffeomorphic to standard one. Okay. Later, he and Michael proved that in 7-dimensional sphere there are exactly 15 diffeomorphism class of substructure. Now we'll say about the tangent space of a manifold. This notion of tangent vector and tangent space in a manifold is a very important notion. Okay, I know it is one of the most basic notion in differential geometry. First, we'll talk about the tangent vector in Euclidean space. Tangent vector in Rn is a vector with starting point x and starting point x. Okay. Then this vector is called tangent vector at that point x. As set of all tangent vector is denoted by p of x in R. And this tangent vector can easily seen that this tangent vector collection of tangent vectors forms an n-dimensional vector space. Now since this is an n-dimensional vector space, so there is a basis. There is lots of basis, but we have standardized one basis. This is called standard basis for Txrn, and this basis is denoted by del of del x1 or del of del xn. So hence, if we have a vector v of Txrn, so v can be expressed as a linear combination of these two vectors. So v is a1 del x1 plus del an del xn, where a1 an are scalar. A tangent vector can also be seen as a derivation of a smooth function. Okay. So tangent vector v gives a map from C infinity Rn. This C infinity Rn means set of all smooth map from Rn to R. Okay. So here v acts on a function f like a1 del f del x1 plus an del xn. Basically here the vector v acting on the function like the directional derivative of a function in the direction of v. Now this previous function v of f has the following property. The first one is the linear property, second also is called linear property, and third one is called product rule. The first one is v of f plus equal to pf plus vg, and second one v of af equal to a v of f. Here a is the scalar, it's a real number. The third one is v of f into z equal to v of f g of y plus f of y into v of g. Okay. Now we introduce the notion of tangent vector to a Gian manifold. Now we use the same condition of the previous mapping. Okay. And the tangent vector of M, where M is a smooth manifold, if at the point P, if a map V which acts on set of all smooth function in M to R, satisfies the following condition. The first one is the linearity condition, where V of F plus equal to V of A plus V of G. The second one is V of AF equal to A of VG, A of V of F. Here is the real number, and the third one is the V of F into G equal to V of F into V of Y plus F of Y into V of G, where F and G are arbitrary smooth function in M and A is a real number. Then V is said to be a determinant vector to M at the point P.